Section 3.1, Part 2. So second idea with energy that we're going to look at is the fact that there's different forms of energy. So there's two main types of energy. So all energy can be classified as either kinetic energy or potential energy, and then we can sort it further kind of within those two categories. So kinetic energy is the energy of motion. So anything moving has kinetic energy. So car driving down the road, baseball being pitched, whatever. Anything that is moving has kinetic energy. Potential energy is stored energy that an object has as a result of its condition and its position. So if you have a pencil sitting on the edge of a table, it's above the ground, it could potentially fall, so it has potential energy. If something's already on the ground, then it doesn't have potential energy because it's, or at least due to its position, because it's not going to fall any further because it's already there. It is possible for an object to have both kinetic and potential energy, so it's not an either or situation at the same time. So a mountain bike rider has kinetic energy because she's moving, and also potential energy because she's above the ground or going downhill. So this is just the tail end of the diagram that you have on page 152 in your notes. We're going to get to the whole thing in just a minute. We're just going to kind of break it down a little bit first. So energy can be represented in a pie chart. This is not in your notes, but it's just sort of like a good way to visualize things. So if you're having problems kind of picturing it, it's not a bad way to work from. You don't have to do this though. So if kinetic energy is Ke and potential energy is Pe, so generally not the way we abbreviate it, but makes sort of sense in context. So halfway down the hill, a rider should be half kinetic energy and half potential energy. Okay, so total amount of energy is represented by the circle, and then the proportion of it, that is one or the other, is where we draw our lines. Okay, let's get not in your notes, just a little bit of a thought experiment here. Okay, so if you look at this guy holding a rather sizable rock up at about his head level, so fairly high off the ground, and then he lets go of it. So we're going to look at what happens to this rock and its energy. So the pie chart, the circle, represents the total amount of energy, which does not change unless energy is actually removed from or added to the system. So potential energy, which is what we have when the rock is not moving, but positionally is in a place where it could move, so being held above the ground, can be converted to energy when the rock is falling. And then at the very bottom, we say that the potential energy is equal to the kinetic energy. So at the very top, our pie chart is going to be all potential energy, and this is more accurately how we would normally represent this. When it is halfway down, it is lost. It now has half its potential energy because it is half as high off the ground, so half the height, half the energy due to potential energy, and therefore the rest of that energy, making it that pie chart within our system, is going to be kinetic energy. And then at the bottom, it doesn't have any potential energy anymore because it's at the bottom, which means all of that energy is now kinetic energy. So at the very bottom, the potential energy is equal to the kinetic energy. And this is like nanoseconds before it hits the ground. Once it actually hits the ground, then it's not moving anymore, and the energy is being converted to other things like the sound of it smacking the ground and potentially some heat energy and various other things. But like right before it hits the ground, it's all kinetic energy. Okay, so now we're back to the diagram that's in your notes. So here's our mountain biker. Okay, so here she is on the ground. And I'm going to go backwards, kind of right to left on this, just because that's the direction the cyclist is facing in the picture. So at the beginning of this sequence, she's on the ground, okay, which means she doesn't have any potential energy, but she does have kinetic energy because we know she's moving because otherwise she'd be falling over because that's how bikes work. Okay, once she gets about halfway up the hill, she's going to have half kinetic energy and half potential energy because half of that energy will have been converted into potential energy to get her up the hill. Up here, she basically has all potential energy. So if we look at the very, very, once again, like nanosecond kind of thing, that she's at the top, she has basically stopped moving in the up-down direction. Okay. And then on our way back down, once again, so we're at that halfway point again, we now have half potential energy and half kinetic energy again. Okay. Huge oversimplification. Does not consider friction, heat, sound, energy moving out of the system, anything else that could be a form of energy in here. It's just simply looking at her, like her positional energy. Okay, so Venn diagram. Take a moment, okay, and pause this if you need more time, but figure out basically where all these different keywords kind of fit in. So energy of position, energy, law of conservation of energy, energy of motion, ball sitting on a table, ability to do work, ball rolling off table, water being held behind a dam, a waterfall, the general phrase cannot be created or destroyed, chemical change, chemical energy in food, stretch rubber band, hot tea. So think about whether these things have kinetic energy or potential energy or both. Okay, sort them into it. Take a few minutes, as long as you need. As I said, highly recommend pausing, because otherwise this video is going to be really long and it's just going to be me sitting in silence. And then we'll take a look at it. Okay, so Venn diagram. The ones that are energy of position, or sorry, the ones that are potential energy of position, the water being held behind a dam, okay, the chemical energy in food, a stretched rubber band. The ones that should be just kinetic energy would be our energy of motion, a ball rolling off the table, a waterfall, sorry, my lines are a little shifted, and a hot tea. And then our potential energy, or sorry, our both would be looking at energy in general, along with conservation of energy in general, the ability to do work, the idea that energy cannot be created or destroyed, that is the law of conservation of energy itself. So those should be in our both category. Okay, page 203 in your textbook, section 3.1 of your textbook is up on Teams under files. So first one's been done for you. So mechanical kinetic energy is a type of kinetic energy, and then it has a description. So mechanical energy means the motion of objects that are larger than molecules, and then some examples. So you're going to go through with each of the types of kinetic energy and fill this out. And then we're going to do the same thing with potential energy. Okay? And so there's more types of potential energy to consider than there are kinetic energy. So you're going to do that as well.